Now let's use our variables and parameters to precisely formulate our objective function. So our objective is to minimize the total cost, which is the sum of the three things: office rent, traveling cost, and engineer hosting costs. So let's take a look at each of them. So for each location, we're going to ask ourselves whether we build a facility there. If xjk is 0 for all the levels, then we don't pay anything. Okay? But if we choose one of the levels, then xjk would be 1, and then we pay that corresponding fjk. Okay? So according to the level you choose, then you pay that particular fixed cost, fixed office rent. And then for traveling cost, whenever you see a pair of ij such that yij is 1, that means you assign customer I to facility j, and then you need to travel hi that many of times, and for each traveling, you pay dij as per service cost. So the sum of all these things is the total service cost we pay for all customers. And finally, you assign engineers. If wj is the number of engineers you hire at facility j, then for each of them, you pay cj as the utility cost, as the cost for hosting an engineer there. So the last term is the engineering hosting cost. And then let's take a look at constraints one by one. For each location, we may choose at most one scale level, and choosing no scale level means building nothing. So we write down our formulations in this way, and this in some sense is a nice way to combine the construction decision and the scale level selection decision. So somehow for each location, you need to choose among all those levels, you choose one. If you choose nothing, that means you don't build anything there. Okay, so that's constraint 1. And then for constraint 2, for each customer and each location, only a built facility may serve customers. So what does that mean? For each customer and each location, first you ask yourself whether any level is chosen in that particular location. If yes, the right-hand side would be 1, and that means you are allowed to assign customer I to facility J. If the right-hand side, on the other hand, is 0, then you cannot assign customer I to facility J. So the second constraint is to enforce that you may only assign customers to built facilities. Constraint 3, for each customer, a customer may be served and must be served by a close enough facility. Okay, so for each customer, we take a look at all those facilities. There must be one facility that is open. Okay, so this is aij, this is small aij. Okay, it must be open, and it must be the customer's assigned facilities together. There must be there must be exactly one facility that is assigned to the customer and that is close enough. We need to have one close enough facility to be assigned to a customer. And then for each facility, the number of engineers that you allocate there cannot be larger than its capacity. So according to the scale level you choose, you know how many engineers you may host there. The number of engineers you allocate there cannot be greater than that. Finally, for each facility, there must be some kind of capacity constraints. So the left-hand side here somehow means the number of engineers you may hire, the number of engineers you hire. Okay, so S is here, I'm sorry. So according to the number of engineers you hire, multiply it by S, that's going to be the total number of services that this facility may complete in a year. Okay, so once you know this number, then the total number of assigned customers, those assigned customers, each of them is going to bring HI events to these facilities, and the total number of assigned services cannot be greater than the total number of services that this facility may complete. Okay, so that's about capacities. And finally, all these decisions are binaries. So whether to choose a specific level, whether to build a facility, that's a binary decision. And whether to assign this customer to facility J or not, that's also a binary decision. So collecting all of them, that's our mathematical model. So once you have a mathematical model, then that's a description. You build a mathematical model only with pen and paper. Then you may give that for someone to build a computer model. A computer model, in our case, we write Python to invoke Groby optimizer. That's enough for us to find an optimal solution. Maybe you would also try to use MS Excel solver, but unfortunately, for our problem, there are too many decision variables, too many constraints, so it does not work. Maybe Groby optimizer is a better choice. So actually, in practice, it's rare for practical problems that can be formulated and solved with MS Excel solver. So this is a nice tool for teaching. Okay, in classes, it's nice to use MS Excel solvers for beginners to learn OR. But to make practical use, those commercial solvers like Groby optimizers may be a better choice. Okay, so being able to write some programs to invoke your optimization engines is always a nice skill to have if you try to become an operations researcher.